Hi, Dr. Revis here with Watch Me Work It. Assigning quantum number values. Watch me work it. Quantum numbers describe the energy, orientation, location, and pairing of electrons in an atom, in an element. In other words, it's a way of describing what's happening to electrons within an element or an atom. And it's described using four numbers. N is the principal quantum number, and it's a periodic table period, row 1 through 7. In other words, if you were on row 1, then that will refer to a value of 1. Okay? L is the angular momentum, or basically it's the orbitals. It really describes whether it's an S, a P, a D, or an F orbital, where an S is 0, P has a value of 1, D has a value of 2, and F has a value of 3. ML is the radial node. It's plus or minus L values. In other words, it's related to the angular momentum. It deals with the orientation. If S has a value of 0, P is plus or minus 1 through to 0. D equals plus or minus 2 through to 0, which means plus or minus 2, plus or minus 1, 0. F is plus or minus 3 through to 0, which means plus or minus 3, plus or minus 2, plus or minus 1, and 0. And then MS describes the spin. An up spin for the last electron in is plus 1. A down arrow for the last electron in is a negative 1/2. So again, let me repeat. An up arrow is plus 1/2, not plus 1, but plus 1/2. A down arrow is minus 1/2. Now, when we look at these radial nodes, another way to describe them is by saying that they show you the last electron in location, and actually not just the last electron in, but it actually shows you the location of all the electrons in. But in many instances, in many cases, you'll be asked about what's the last electron in. Okay? So for an S, we have a 0 location. There's no nodes in a S orbital, which looks like a sphere. For a P orbital, we have this 0 center, and then to each side of the center, we have a minus 1 and a plus 1. For the D, we have our center position, a minus 1 position, a minus 2 position, and a plus 1 and a plus 2 position or location. For the F, we have our 0 position where electrons can reside, and then we have a minus 1, minus 2, minus 3 where electrons can reside. Then we have plus 1, plus 2, and plus 3 where electrons can reside. So essentially, these electron locations are residents, if you will, or locations where the electrons can reside. All right? So now, let's take a look and work a problem to show you a little bit more about this. Now, when we talk about quantum numbers, we have to talk about the electronic configuration. An electronic configuration is simply a description of where electrons are on the periodic table. Now, you can summarize that in what we call the field order shown here. So this is a standard field order for that. And for many people, they will memorize this. However, this field order actually is shown to you and given to you on the periodic table. So you can read it directly from the periodic table. So that's how I'll be doing it when I solve these. Okay, I'll be reading it directly from the periodic table. All right, so let's work through a problem. Let's take carbon. We have carbon. That's our atom. That's our element. If we take carbon, we note that carbon is in row 2. Therefore, it has an N value equal to 2. That's it. All right. If we look for L, we note that the last electron in carbon is in the P orbital. Therefore, its L would be 1. Now we have ML and MS. For ML, we must do the electronic configuration diagram to properly do it. If you've done it enough times, you can actually see the diagram without drawing it out. Let's draw these diagrams out. But before we can draw the diagram out, let's write the full electronic configuration. All right? So the full electronic configuration would be a 1s2 because I have 1s, 1, 2. First row, first period is only s orbital, so hydrogen and helium only need an s orbital. So 1s2. Now we're here for a 2s2, 1, 2. And now carbon has 1, 2 electrons in the p orbital. 2p. This is N2, the row, 2p, 2. So this is electronic configuration. Okay? All right, so we would write that electronic configuration. Let me clean it up a little bit for you. So this is our electronic configuration. This is not the diagram, this is configuration. Note here that the 2, 4, 6 electrons correspond, okay? Oops, not 6. Let's back up. Note that, too quick here, 6 electrons correspond to the 6 electrons equals the atomic number. Okay? So there we have 6 electrons, that's the atomic number. Okay? Just so you also know, the last 2 here, this 2 and this 2 are in the 2. So that's the number of valence electrons. We count the valence electrons by looking at the highest n value and summing the 2 electrons here. You summarize all the electrons to determine the atomic number. Okay? Now, on to ML. Our ML, we're going to do the electronic configuration. So to do electronic configuration, we need to draw out our orbitals here. And this would be a 1s. We don't, by convention, label the 2 above here. And this would be a 2s. We don't write the number of electrons here. And let me move this 2p down because I happen to know I'm going to need a little space there. So I'm going to drop this down just a little bit lower and write it 2p here. So this is a 2p. We have 3 degenerate levels in the 2p. So this is 2p, 3 degenerate levels, 1, 2, 3 degenerate levels. Now, so let's put in our electrons according to Hund's rule. Hund's rule says we can only pair once we've filled all of the degenerates. Since there's only 1s, we can fill it with 2. It's only 1, 2s, we can fill it with 2. With a 2p, we have to distribute 1, 2 across the 2p, because that's 1, 2. Now that we distributed it, that's it. And that gives us our electrons in the 2p. So if we want to describe the ML value, we would go to the center point and then look left and call it minus, look right, call it +1, and that's the description. So the last electron in the 2p is actually in the ML equals to 0. And so that's kind of its location. Is one way to describe it. Okay? The first one electron in, by the way, is in the -1 location, or the -1 ML. The MS then will look at the last electron in. So the last electron in is in the ML0, and its orientation is up. Therefore, we have a MS here. Our MS is equal to +1/2. Okay? Note from this, you can also determine the number of valence electrons from here as well. We can ring these, and we see those are also our valence electrons. Okay? And so this would be our electronic configuration diagram for carbon, and from this we can get our MS +1/2 and ML equals 0. All right? Okay, now let's do another one. Let's do chlorine. Okay, if we have chlorine, right away we see is N equals 3. You know the routine now, so we'll just pick up the pace. And so L, the last electron, is going to be located in P, so that's L equals 1. And we're going to find our ML. I'm going to write the full electronic configuration here, 1s2. I tell you what, I'm not going to write the full one. Let's do the shorthand instead. All right, let's put in neon. Let's start at neon right here, and let's go from there. All right, so we're going to have neon, and once we pass neon, we're going to be at a 3s2. Okay, write that a little cleaner for you. Going to be at a 3s2. That's 1, 2. And chlorine's going to be 1, 2, 3, 4, 5. Be a 3p5. Okay, so if we do this, that's our electronic configuration. And just for fun, you could count the total number of electrons for chlorine. Okay, so we would have our 10 here. 10 plus 7 gives us 17. Electrons, total number of electrons, which also equals the atomic number. Just so you know that. And, you know, we could check these valence electrons by checking the last ones here. When you do the shorthand, it's pretty easy to check the valence electrons. So valence electrons here would be 7, just so you have that information. Okay? All right? So next, let's draw the diagram. This does not give us ML. We need a diagram for ML, and if you've done it enough times, you can probably do it in your head. So here we draw the 3s, and then we have the p. We have to draw all the spaces for the p, even though they're not going to be all filled. Those are the rules because they are degenerate. So we will fill in our 2 electrons here, and by Hund's rule, we would put in 1, 2, 3, 4, 5 here. And since we put in 5 here, okay, we note that we can draw out the ML positions by putting a 0, +1, and a -1. And this means if we design the ML of the last electron in would equal to 0. Not the last electron you see, but the last electron in equals 0. Occasionally we ask different questions about ML. If you ask what's the last low electron to the far right, it would be in the +1. Okay, the only unpaired electron is in the +1. Those types of questions might be asked. All right, so we have the ML, and then we can have the MS and the last electron. Let's do that again. The last electron M for our MS. Again, we're based on the last electron in here. MS, last electron in is in our 0. So I'm just circling the whole thing here. And so that's going to be equal to a -1/2 because it's spin down. All right. Something else worth noting that's occasionally asked is whether or not this is paramagnetic or diamagnetic. This is paramagnetic because this set of orbital is not full. Okay, we have an unpaired electron. Okay, it's paramagnetic when there's an unpaired electron, meaning that it's not full. And you could have did that from the one above because you know the P6 here. Okay, that's -6. Should have 6, you have 5, therefore it's not full. There. Okay, so we had our MS, just to finish this off here, put in all our values so we can see them. ML of the last electron in, just because that's what I'm interested in, and this is going to be a -1/2. All right, let's do one more here. Okay, let's do another one. Ready? So now let's take chromium. So if we take chromium, We can do chromium here, and we know that chromium is located on the fourth period. So that's N equals 4. L is in the D. So L equals 2. Now we'll do our ML and our MS. You can almost do this in your head by now, I'm sure. But we're going to write it all out. So let's write the electronic configuration by starting with argon. Shorthand this one. We'll have argon here. And so now we'll have a 4s1 2. And since we're dealing with chromium here, we know that this is a D, so this is going to be N minus 1 to do D. So we have to subtract, so we have 4, so that's 4 minus 1 equals 3D. So that's going to be our D, so it's going to be a 3D, and we simply count across on the periodic table, 1, 2, 3, 4, or we memorize it from the ribbon. It's up to you. You can use the ribbon, or you can count. I always use the periodic table. So we have this, and so that's our electronic configuration here. All right, and we could total up all these electrons, and we would get a count of the total electrons that would match the atomic number. We know the argon here. Okay, we have the value for argon. It's 17. No, I'm sorry, 18. So argon there is 18. And then we have 18 plus 2 is 20 equals 24 electrons there. So that's the total number of electrons for chromium. That's its atomic number. So we have that just for fun. So let's draw the diagram so we can figure out the ML and the MS. And they're best done from the diagram, but again, if you can do the diagram in your head, you could actually do it straight from the periodic table. All right, so for the D, we're going to have 5 degenerate levels for the D. So this is 3D, and this is 4S. We populate our electrons, 1, 2. Hund's rule said put 1 in each before we pair. So we're up to chromium, 3, 4, before we pair. So there we have chromium here. And since we have chromium, we can now put in our ML by putting in the positions of 0, find the middle point, and go left, go right, go left, go right. And we know our last electron here is in the ML equal to +1, and that's the one we're interested in. You can talk about your interest in any of them at any given point. And the spin, this electron is up, so that's a +1/2 when we do that. All right. So that's how we assign quantum numbers to our atoms or to the elements.